All right, we are recording. We will be going over the clicker questions for chapters 6 and 7. We'll be going over like the first few just to get the general sense of each chapter. And then we'll skip past and do a harder question from each of them to see if we can test ourselves. All right, so we're starting off with chapter 6. Let's just scroll down to the first question and see how we do. All right, question 6.1, I'm just gonna read it out loud. And then after a second, we can discuss and see what our general thoughts on what the answer might be is. All right, so the question is, an elevator is being lifted at a constant speed by a steel cable attached to an electric motor. Which of the statements are correct? I'm not gonna read those out loud, but you can see from down below. I'm sharing my screen. So yeah, let's just get this started. I'm not going to answer it immediately because I'm still deciding. But one thing we can note at first is that there's two entities, a cable and the elevator, and the elevator is being lifted at a constant speed, right? So the velocity is a constant speed that is going upwards, and the cable is doing that to the elevator. Does anyone want to tackle this one first?
Well, automatically going off what you said, the cable would have positive work.
All right, yes. All right, perfect. So if we look at our answers, we can look and see which one of these says the cable does positive work. A says that one, and B say that. So we're looking at A and B for the cable does positive work. Now it says between the two, does the elevator have positive work on the cable or does the elevator have negative work on the cable?
I would say it has negative work on the cable due to weight. And since the positive direction is upwards, then yeah, the elevator, it's exerting negative work on the cable.
Okay,
I agree with Alexandra.
Yeah, I agree with that because if the cable is moving in one direction, the elevator is inhibiting its ability to move in that direction. So that would cause a negative work on the cable. So I feel like we're leaning towards B. Does anyone have to add anything, or are we just good on B? Does anyone disagree?
No, I agree with that.
All right, perfect. So we're gonna scroll down, we're gonna see if our answer is correct. And it looks like we are. So yeah, just to reiterate, if the cable is moving in upwards direction, having positive work on the elevator and lifting it, the elevator's weight and the force caused on it by gravity will cause the cable to not move as freely, being a downward force, causing there to be a negative work, specifically since it's in the opposite direction. So we'll go on to our next question. Question 6.2, I'll read it aloud. An elevator is being lowered at a constant speed by a steel cable attached to an electric motor. Which statement is correct? Before we jump in, it's important to note that this question is kind of the opposite of the last one. It's talking about an elevator being lowered instead of lifted, and the velocity is going downwards at a constant rate. So how are we feeling about this one?
I automatically would think it would be the inverse.
Exactly.
Yeah,
I agree with that.
So flat out the inverse. Does anyone want to talk to me about how this happens in the same way that we know that when the cable goes up, the elevator pulls down on it from the last example? What's happening here?
But this time the positive direction was moving downwards.
Okay, exactly. So that'll cause it to be the opposite. So if we're saying that in this situation, the cable, if it's the opposite, it would be going the negative direction. And if it was the opposite for the elevator, that'd be going the positive. So our answer in this situation would be C.
Yes, agreed.
Okay, we agree on that, which is lovely. So if I had to describe this, I would say that in this situation, the cable, the elevator is going down at a certain rate, which we can assume will be lower than the speed of how it would fall in free fall. And the reason that is because the cable has tension against the elevator that causes it to be hoisted at a slower rate. So instead of just falling normally, it'll be lowered down at a slower rate because the cable exists and is tugging on the elevator. But even though it's allowing it for it to go down, it won't be going down at that same pace, causing there to be a
and it's also not going at the exact speed of gravity as well, because I know gravity is going to be working on it too. Because of that, there's going to be a lot of tension on that rope.
Exactly.
So definitely agree. I was gonna try to add some, but you got it complete.
All right, and we are correct. It is C. So now we can tackle 6.3. All right, just looking at that question, we see that it's a 2 ice boats question, always fun. So 6.3 says that 2 ice boats, one of mass m and one of mass 2m, so one is double the mass of the other one, holds a race on a frictionless horizontal frozen lake. Both ice boats start from rest, and the wind exerts the same constant force on both ice boats. Which ice boat crosses the finish line with more kinetic energy? All right, so looking at this problem, there's 2 things we can note. One being that the mass of the second boat is twice the mass of the first one, and that the kinetic energy that they start at will, since it says that they're exerted by the same like wind force, that's a constant force, that means that the kinetic energy in the beginning will be the same for them. And it's asking us for the kinetic energy final. Anyone want to tackle this one? Or say which answer they like the most?
I feel like they would end up having the same kinetic energy, you know, not just the fact that it's on a frictionless lake of ice. It says the wind exerts the same constant force on them. Normally, because of the different weights, you'd expect it to, you know, need more force to get it moving. But that's the thing, it needs more force to get it moving, not to keep it going, you know. So that's why I feel like it would be. Might be wrong.
Yeah. And it's important to note that in situations like this, since it's frictionless, that means there's no other primary force aside from that, like pulling it back. Like there's no friction force that's deterring the horizontal force on the boats. And since they're both on the ice and neither of them is falling, that means that they're at equilibrium in terms of the y direction, right? The normal force and the regular force are acting, the normal force and their gravitational weight are acting in the same way, even though they're like one is more massive than the other. So if there's no friction and there's no like the weight doesn't slow down either of the boats in the situation because there's no friction and there's like an equal between their weight and normal force. That means that if their initial force added onto them is the same, that means their initial kinetic energy will also be the same, which means that they will just have a consistent like energy, which means that their kinetic energy at final should also be the same. So I'd be inclined to go with E as well. Anyone want to add to that or no?
I'm so sorry. It's just that I have people in my house, so it's like I gotta turn camera on and off.
And
Same thing with the mics. I'm so sorry about that. But I'm here the whole time. Trust. The way I look at this is really with speed, and that's where I first start. Speed and velocity. Velocity is not really an impact because it would be going in the same direction. But then you look at the force, and then you look at the weight. You realize that one of them, of course, would enter the finish line before the other one. But the force is the same. So force being the same, that's where I'd get the kinetic energy being the same as well. Now, the displacement between the time required for that displacement could vary depending on mass. But in this example, and especially how you were explaining with no friction, kinetic energy would remain the same for both. That's how I see it. Exactly. A little different perspective from you guys, but.
No, but yeah, I get you, because like it's not a question of like which gets to the finish line at what time or faster. It's just asking for the energy being acted on the object, or that the object has.
Well, wasn't kinetic energy proportional to mass, meaning that if mass is greater than kinetic energy, it's twice or 4 times, actually 4 times as much.
Right? I agree with you. Yeah, it did. I remember seeing something similar like that, and it did say the exact same thing you did. But I guess in this case, they will still be going at different speeds, though. That's the thing. It didn't say which one will reach, will finish the line first. That's not what it's asking. It's asking which one would have more kinetic energy at the end. And so that's the reason why it's still E, although they would still end up, one of them is going to reach the end first because it has less weight, meaning that small amount of let's say force that acts on them will do more. It will just have more work on more impact on the smaller one, if that makes sense. But and also because of the fact that it's frictionless too, that comes into play. So I agree with you, and I do remember seeing that in one of the practices. It was either an example or something like a clicker, but I'm not sure.
Well, from what I remember, like if they had the same amount of forces, that'll like attribute to like a difference in their accelerations. Because if we remember like from a past chapter, force is equal to mass times acceleration, right? So we know that they have the same force, but one of them is double the mass, which means it'll have half the acceleration, right? But like that's not really what the question is asking. It's just asking for its in the amount of force it ends with. So we know that if they have the same force, that means that the work total should be similar, and work total is your final minus your initial. And we know that they have their same initial force because of that, what they give us. So if the kinetic energy in the beginning is the same, the kinetic energy in the final should be the same since they're on a frictionless plane. So I'm down with E, but if we have a disagreement, we can check.
Seems like David and George accidentally got kicked out. I keep getting kicked out as well. And so that's why I got my camera closed, because it sometimes might do the same thing, but I'm still here with you guys.
I hope that's not my connection.
No, it's not yours. Most definitely not yours. It's mine.
All right. So let's just roll with C and we'll check and then we'll discuss. So it's looking like C. Hopefully George and David join back soon. Computer problems are going to happen all the time. So it is E, which is looking good. Do we have any more questions? No, that's fine. We'll move on to 6.4 now, and we'll just do our best. All right, so 6.4 reads, a tractor driving at a constant speed pulls a sled loaded with firewood. There is friction between the sled and the road. The total work done by the sled after it has moved distance D is, it's asking for total work.
The total work, interesting. So we might have to do that FD cosine formula thing again.
Yeah.
Because this one has an angle. The theta is not like, it's not 180 or 0. And so this angle might end up, being a little different. But I speculate for this, the total work moved after the distance, considering there is friction. So we'll have to, add in friction as well. Also, if you can do at the same time, try to do the free diagram. So that might be a little too much, but I don't know if you could do that.
I can do, like if we do this, we have this be our angle. The force is
and then
going,
you got friction pulling in the opposite direction on the x-axis.
Yeah. So we have our F here. This would be the tension.
And then you got S. And then S going to the right.
Yeah, our S would be like here, just as a vector. But we don't really know. We know that this speed is constant, but we don't know what it is, right? There's a friction between the sled and the road caused right here. This is the free body diagram of the sled.
Wait, real quick. What was it? How do you calculate the force of friction again? Wasn't it the coefficient of friction times gravity or something? Times mass times gravity, something like that? Or was it times the amount of force added?
I don't remember off the top of my head. There are friction between the sled and the road. The total work done after the sled has...
How do you calculate the force of gravity?
He was asking for...
Oh, not the force of gravity. How do you calculate the force
of friction?
Friction. Yes, because if they give you the coefficient of friction, because I feel like this might be on the exam, like if they give you the coefficient of friction, and they give you other details as well, and you have to factor that friction force into one of the forces, so basically into F, as one of the forces in there. How would we do that? Because I do remember there was one in which it showed mu times N, and I don't remember if N was like the amount of newtons of force being pulled on the object or something like that, but I think that's what it was, but I'm not too sure. I don't know if you have any better idea, Alexandra.
I'm just like looking for how to calculate the force of friction. Let me double check. I have the slides here.
While she's doing
But
that,
oh right, I don't think I answered. I feel like it would be positive work.
positive
Well,
work.
actually, wait a minute. It says the total work on the sled. And I remember friction is proportional to weight and force. So for example, like the more you pull something along, the more force there is, the more friction force there is.
That is
But
true.
the friction force will never be more, than the force pulling it because it's still moving. If the friction force was more, then it would not move at all. So I don't know. I'm gonna still stick with my positive statement, but I also feel like it could very much be negative because it's kind of like that, that like gravity one where it's going in the opposite direction, where the force being applied is going in the opposite direction, but the displacement is in the opposite. So it might depend. I don't know what you guys think of this.
You guys, I'm so sorry about that. My internet at the house kind of cut out, so I had to come outside on my phone. But couldn't it also couldn't the work also be zero?
That's what I was leaning towards, but
this is my this is my thought process on this one. I know it might be out of left
field. You're totally right.
But
and why would it be zero?
I'm not.
I think I know why. Wait. What's the cosine of
thing is, we don't have any
so
numbers.
we would calculate work is equal to the magnitude of vector F, which in this case is
that'd be the force of
distance T, right?
Oh yeah.
Cosine of no times magnitude of S, cosine of the angle.
The reason I said sorry if I'm interrupting. The reason I said I didn't know why George said it would be zero, because I do remember there was some in which in the examples, right? They were going over them.
I do see why. I'm looking at the slides.
Yeah, if you get zero, like because of the angle or something, like if you plug it into cosine and then the answer becomes zero, no matter what force or no matter what displacement you multiply it by, it would be zero. You see what I mean, Alexandra?
Yeah. And also, because the angle, because it's displacing in a horizontal way.
Yes, right.
Exactly. And we have as well.
And in this case, like being the angle, it's pulling the firewood up, and like an upward motion, so there's no work.
Yeah.
According to the slides, says when the force is perpendicular to the direction of the displacement, the force does no work on the object.
Okay, so if it's being pulled up and the displacement is to the right or to the left, basically perpendicular. Oh, that's what perpendicular is. Okay.
But yeah, so
see how we did.
Okay, I think I'm following. George, will you say something?
Oh, I was just saying, let's see how we did.
Yeah. All right. So if we were to say C here, we can just go ahead and check. Do this. And it is zero.
Yes. Okay, good stuff, George.
I had to think back to that example.
Yeah. And thanks, Alexander, for bringing that one up, because I forgot. If it's going in a different direction and the force is like not opposite to it, but up in perpendicular format, it's always going to be zero work. And you're right.
Exactly.
All right. So now we're on our one of our final examples for chapter 6. So 6.5 says a non-zero net force acts upon an object. Which of the following quantities should be constant? So if it's saying just any force that's not zero, so if any like actual force acts on an object, which quantities could be constant? Realistically, any of them, because the velocity won't particularly be changed. Because velocity and speed, first of all, are the same thing. So B and C have to be together.
Right. And the question is about kinetic energy now, because would kinetic energy change as the speed goes along? So wouldn't that couple everything together?
Yeah, this is an easy one, I feel. Because like just by understanding like the definition of speed and velocity in this chapter, like they're the same. That might not be the issue for every chapter, but in this chapter, speed and velocity are the same quantity. Just a different word for the same thing. And kinetic energy is proportional to both to the two of them. So I would say that they could all be transported. All right. Honestly, I think we snapped this question already. I'm thinking it's D.
Yeah, I'm thinking D too. I don't know.
Yeah.
None of A, B, or C.
Yeah, because literally, okay, so
more than A than one of A, B, and C.
It'd be very depressing if it was actually E. But we're just gonna.
Yeah, it would be kind of sad because we feel so confident.
Yeah, I'm like this. I'm like, I got this. I'm the man, and then it's gonna be E. So I'm gonna check just for my own pride. It's D. Okay.
Let's check. Oh, it is. Okay, good.
All right. No L is being taken today. I'm happy about that.
Not today.
Not today. All right. That's a good feeling. So someone's annotating.
Yeah, I'm sorry. I thought I could do this on my phone, bro. I thought I was just doing it from my screen.
No, that's fine. But no, it's not. But yeah, that'll show. So honestly, if any of y'all want to draw, you can always annotate. Happy to see. But
yeah, I feel bad because you're always the one drawing and talking. So I was like, man, I could draw on this for them.
Yeah, so go nuts if you ever feel like it.
For sure.
Do you guys want to do one more from chapter 6? You just want to hop to chapter 7? I know we've been here a while.
Yeah, I think chapter 7. We can go ahead.
All right, so now we're gonna be moving on to chapter 7. Does anyone have a time check, or are we just chilling?
Oh, we've been here for like, I don't know.
We've been here a long time, long enough.
Definitely.
All right, so now that we're moving on to chapter 7, let's just tackle it, do our best. All right, so, okay, this seems easy, hopefully. It might not be. All right, so question 7.1 says a piece of fruit falls straight down. As it falls, and then it gives us our options. So this is talking about force as well as potential energy. So if we look at this, it says that either it's talking about gravitational force and potential energy. So when something falls, that means that its acceleration is pointing down, its velocity is going down. So in that situation, downwards is the. But is someone gonna say something?
No.
Okay.
I'm so sorry. That was trying to connect.
There's two Georges.
Yeah, I think he's on his phone and his computer. He's trying to.
Oh, also, I think we can cancel out anything that says potential energy increase, because if the lower something goes, the less potential energy it has. I don't know if you get that. For example, ignore the fact that it's moving. Yeah.
So let's say we had this apple, right?
Yeah.
We had this apple, right? And we had an apple down here, right? And this is, let me get a different color. Let's say
I can draw it for you. Since I got
this is the ground, right? The potential energy caused by gravity for this apple, let's just say it's demarcated by the distance. This is how much this apple can fall, right? Versus this apple falling, right? So the closer you get to the ground, the lower your gravitational potential energy is.
True.
Right?
So
that's how I would go about it too.
And then one thing.
Well, that would be like the first half at least.
Yeah. And then one thing that we know for a fact is, since it's falling straight down, we know that in this situation, the direction of gravity is the positive direction, right? So we know that our velocity is going down this way, and that's positive. So the positive velocity down, right? Gravity is an acceleration downwards, right? So the gravitational force, if the apple is falling like this one, should be becoming positive, right? So anyone want to tell me which answer is this?
I would say B, the gravitational force does positive work on it, and the gravitational potential energy decreases.
Agreed. And because the gravitational force also pulls it down, and it's going down as well, so they're going in the same direction. So it's
Mhm.
definitely going to be going positive. I guess one way to remember it is, if they go together, it's a good thing, it's positive. But if they're going against each other, it's negative. I don't know if that applies for everything, but that kind of helps in this case.
And we're correct. It's B. So good job, y'all. We can now look at 7.2. Oh, this one looks scary.
Ooh, let me try this one. Let me see if I can
Yeah,
go
so
to
you can,
this.
someone want to read this for me?
Yeah, I got you. You toss a 0.150 kilogram baseball straight upwards so that it leaves your hand moving at 20 meters per second. The ball reaches a maximum height of y2. What is the speed of the ball when it is at height of y2 divided by 2? I guess it's asking divided by 2, ignoring air resistance. So I guess it should still be 0. Well, no. Actually, never mind. I thought it was asking for the speed.
Nah, when it says, what is the speed at y2? Wait a minute. What is this?
So we see y2 is the one, the higher one.
Yeah.
Yeah.
For what is
divided by 2.
So I feel like it
Ignore
should
air
still be 0, right? Because it's like, if you
No.
throw something up, gravity is gonna act on it, and it's
its
gonna reach a
maximum
stop.
I
height,
think
it would be
I
basically
actually
weightless.
think it's B1 velocity. B1 divided by 2.
Well, the one thing I have, wait, when the ball is at y2 over 2. So halfway to y2. So if it says y2 over 2, is it saying like here?
Exactly.
So it's asking
Because
for
if you think about it, the ball, it's going downward, the opposite to y1, which is already all the way down. So halfway of that, it will be 10 meters per second.
Yeah,
I thought it was saying. Oh, go ahead.
I would say like, yeah, it would. Yeah, I would say 10 too. Like it would have to be at least 10. Because if it's at this halfway point, if we're ignoring air resistance,
or using midpoint.
Yeah, I would. Yeah, if I was just eyeballing this, I think the midpoint, and then that would be 10, right?
But okay, hold on. I don't know. I'm not too sure, because at first I thought it was asking like the height it reaches just divided by 2, since y2 is the height, like
it's asking
divided.
It's asking
by the
it's asking for speed. So we look at velocity, correct? Yeah. Velocity True. 1 is 20, and if velocity 2 is 0, we want to know halfway of the height of the velocity. It would be 10 meters per second.
All right. So I'm looking so confused at A.
Because
oh, who is talking? I'm sorry.
Oh, no, I was just gonna say, I don't know why I'm so confused. It's probably because I was expecting that it's asking, at the height, not even that it's asking.
I know exactly what you mean. Kind of like when the slope is 0 is what it's asking.
Yes, kind of like that, where it reaches the peak, and then it's not going up or down, and it's just 0. So, you know what I mean?
And you're automatically thinking 0.
Yeah, because it's like not going to be.
I couldn't agree more. 0 slope.
Yeah, but I was thinking like it would still be at the height, and not thinking the midpoint of the height. But you get what I mean, George?
Exactly. 100%, 100%. But then, as soon as you try to factor in the potential energy and kinetic energy, is when you kind of realize that wait, it can't be 0.
Yeah.
So, I think me and Alexandra are leaning towards 10, or I mean maybe C.
I agree with you guys. I think it has to be at least 10. At least 10.
All right, so we're at the A or C area. Let's just check it, because like they're like
I'm just saying at least 10.
Yeah. So they're almost.
You would have to divide by 2. So yeah.
Exactly. If we're just going by midpoints, it would either be A or C. Let's just check it. And it's C, and that like makes sense. Like my reason, like I put like A just for midpoints, but like C makes sense because we're kind of making an approximation in that sense. Like there's no way to tell if it would be exactly 10 meters per second
Excuse me.
if we were ignoring air resistance at that point.
I'm sorry, I couldn't hear you. My internet was cutting out.
You're okay. What I said is like C does make sense. Like I just said 10.
I'm so sorry, I couldn't hear you. What were you saying?
Oh, okay. So what I was saying is that C does make sense. I said 10, which is A, but like I can see why it's C because like it needs to be 10 meters per second at minimum to like make like that makes sense. Because like it couldn't be exactly 10 because of the mass, which is not like 1 exactly. So it needed to be greater than 10. Wouldn't be a precise number.
I agree. Yeah, I agree. Because if we look at the formula for speed, I'm sorry. It's
Me too. Go ahead.
it would be speed equals distance over time.
Mhm.
So it's not dependent on mass at all. But taking into consideration that we're calculating velocity, using velocity, it would be the ratio is equal to distance over delta t.
Are you looking at something?
Well, I do think that one makes more sense than all of the others.
So we
I
have
agree. Definitely with common sense, that's the answer I would go with. If it would come down to figuring out the values, I think me personally, I'd probably have to dig into the formula a little bit more and really figure out which one would be adequate for this problem.
Yeah, a good thing it's not asking for a precise number. It's just asking for a general take. So we move on to 7.3. A ball of mass M sits atop a table. The tabletop distance D above the ground is D above the ground. The gravitational potential energy for the ball is equal to, this is subjective because gravitational potential energy depends on what you're saying that the ball will fall to. So if you said that the ball were to fall to the table, then it's 0 because everything has a gravitational pull to it. Typically we standardize it as the ground, right? Because that's about like as far as you can drop. But realistically, I could see it be any of these. Does anyone think it's one in specific?
No, I agree. It's a matter of perspective.
So you said it's 0?
No, I said
it's any value you choose.
I mean, maybe it's 0. I don't know. I think it could be any one of the 3. I think it could be anything you choose. Like it could be 0 in a situation where the gravitational potential energy is relative to the table.
Wait, but the reason I was asking, I don't know. I feel like it couldn't be any value you choose. I feel like it could be 0 mainly because there's no chance of the ball touching the ground straight through the table.
Exactly.
Yeah, but remember that you'd always have
Go ahead.
So they're talking about gravitational potential energy. Oh, sorry.
No, I was literally, I think we were gonna say the same thing.
The same thing. So they're mentioning gravitational potential energy. So we know that gravity is involved in the equation. So I would say it's either A or C, but since the ball is moving downwards in a positive direction, in terms of, or compared to distance, I would say it's a positive M times G times D.
All right, I hear that, But I'm gonna bring out the tomatoes again. You guys remember the tomatoes?
100%.
The apples. The apples.
The apples, that's what they
apples.
were. Mine looked like tomatoes, right? So hold on, I'm gonna use a different.
The way I'm thinking about it is this, right? What would be the difference between, I'm so sorry about that weird.
Go for it. Draw whatever you need to. I'm gonna draw
Right,
my
so
over here.
for me, it's really the difference between all right, don't worry so much about my ledge. I know it's terrible, but you guys get the point, right? So this right here is the most important part.
Yeah.
Which is it's like your reference line. It's like the level that you're referencing to. You know what I mean? So it's like a reference level.
Yeah.
And if the reference level can change, then this itself can change, because this distance right here would change.
Yeah.
That's how I see it, at least.
So in the situation that your reference line is the table, your gravitational potential energy would be 0 or closely approaching 0. But if it was the floor, then you'd have mass times gravity. Right? Is that what you're saying? Because let's say that, like, using that example.
I'm sorry. You were saying? Sorry.
So in the situation. Yeah. Okay. So you can hear me, right?
Yes.
Okay. I'll try and speak slowly. So in this situation.
No, you're okay. It's the lag between me because I'm outside, so it's terrible. But I can hear you. So
in this situation where your line of reference, like you were saying, is the table. Right. So let's say this is my line of reference. That would make my gravitational potential energy as small as possible, right? So either 0 or approaching 0. But if my line of reference was the floor, we would say that it's whatever the mass of this is times gravity times this distance, right?
Exactly.
But then you can look at it the other way, saying that since it's going down, right, and the ball is being like neutral forced up, right? If we drew a free body diagram, you could say that this is also negative mgd. So I think that it's any one of these values, because like at the very least 2 of them. Because we see here that if we use a reference line to be 0, then it would, to be the table, it'd be 0. But if we use a reference line to be mgd, to be the floor, it'd be mgd. So I think it's any value we choose. But if you think it's a specific one, then state your piece.
I agree with you.
I'm just looking forward to seeing what it is.
Yeah. Let's just check it, because that's what matters, that we learn. Let me get this. Oh no, wrong one. Okay, it is D. And it's because, like what George said, it depends on what you consider the floor to be.
And that is the reference
level.
The reference level.
Yeah, whatever you consider the ball to be getting pulled to. So if it's a floor, it has a bigger gravitational potential energy. But if it's just going to land on the table, then if it's touching the table, then it's just going to be 0 because it has no potential of falling. That's how I like to look at gravitational potential energy. It's a potential of it falling. If it's already on the floor, it can't fall. Ooh, this one looks weird.
Yeah, that's kind of like what I thought originally, because I was like, it can't fall if something's holding it from it.
Yeah.
And so I thought that would negate the energy, but yeah.
You'll probably see problems like either one of these, where it's asking for the gravity in relation to it falling on the table, or the gravity in relation to it falling on the floor. And you'd have a different gravitational potential energy depending on what it asks you to look for. Oh boy, whoops. Okay, 7.4. As a rock slides from point A to point B along the inside of a frictionless bowl, where mechanical energy is conserved, why does, wait, I'm sorry, did I read this wrong? As a rock slides from A to B along the inside of a frictionless bowl, mechanical energy is conserved. Why does this happen? Ignore air resistance. Why is mechanical energy conserved?
Because why is mechanical energy conserved?
Anyone want to tackle this?
Let's see.
I'm so sorry. I'm just put some thought into it.
If you have trouble speaking, if you're lagging, you can just like circle what you think. If I'm looking at this, so if mechanical energy is conserved, that means that from at point A, the kinetic energy, right? So the kinetic energy is equal to some number, right? And the potential energy is also equal to a number. And they add up to something that's mechanical energy, right? That's a mechanical energy at A. The mechanical energy at B is the same thing, right? That's what we know about conservation of mechanical energy. The total amount of energy at A is the same as the one at B. However, let's say that in this situation, kinetic energy was 2 and this was 1. We could have a potential energy here of 3 and a kinetic energy of 0, so long as they add up to the same number, because 2 plus 1 is 3 and 3 plus 0 is 3. That's what like the law of conservation of mechanical energy essentially says. That no matter what, the total amount of energy in an object will always be the same. So if I was looking at this, I mean, I don't know if that helps me. I'm gonna be honest. I know that to be true. I could say that I would guess that the reason why it stops here is due to some type of normal force that's acting on this that like cancels out these
I agree perpendicularly.
Yeah, okay, they're perpendicular. Okay.
That's what I'm thinking. That's what I'm thinking. I'm thinking of the fact that it's perpendicular, even at point A, the normal force, it's the only force that's really acting on the whole system, like in general.
Yeah.
So the system's not really having like an external force being added, and it'd be just really be like a conservation of energy. So,
well, we can look at it is
at this point, it's
because the velocity is going, I would say, like this way, and that like it's centrifugal, right? So it's going this way, then this way, and this way, until we reach right here. And at this point, the normal force of it is perpendicular to the velocity, which would cause it to, if we remember force times s times cosine theta, when it's perpendicular, the cosine of, in this situation, 90 is 0. So it'd be F times S times 0, which is always 0, which would cause it to stop.
Oh, actually, I'm looking at one of the slides on chapter 7. And it says the conservation of mechanical energy. And it shows the example where the runner jumps and it forms kind of it in a like a inverse bowl type of fashion. So this is the same case, just that it's opposite.
Yeah. And did the
So-
same thing happen there?
Yeah, the same thing happened here. And it says when only the force of gravity does work on a system, the total mechanical energy of that system is conserved.
Yeah. And
So we
that's
can say that the normal force being exerted by the rock
Perpendicular.
is sort of
it's
like the weight.
perpendicular
Yeah.
to the, exactly, perpendicular to the surface.
Yeah. All right. So perfect. I think we've arrived at D. Let me erase this stuff before we check our answer. And we'll see right now. Okay, it's D. Good job. And we arrived at that together. That felt good. Let's just look at
So let's
this.
keep that in mind, guys, that when the normal force is perpendicular to let's keep that in mind that when the normal force is perpendicular and it's the only other force acting on the system, we'd have a conservation of mechanical energy.
Mhm.
And we can clearly see that it's perpendicular because if you look at point B where the rock is,
Mhm.
it's perpendicular to the surface, to the horizontal part of,
Yeah, to the
the
floor.
wall on
Mhm.
top,
Yeah.
top. Yeah, and the floor.
Yeah, and
Correct.
that's what essentially causes it to stop.
Exactly.
It
Mhm.
essentially takes all the kinetic energy that was there and turns it all
In the
into
bowl.
potential energy. Exactly. So that's what causes it to stop right there. Oh my God, what is this? All right, so I'll just read this one. This one looks scary. All right, so the
That
two
looks like a
ramps,
headache.
yeah, the two ramps shown are both, all right, so the two ramps shown are both frictionless, with heights y1 and y2 for both of them. For each ramp, a block of mass m is released from rest at the left hand of each ramp. Which block arrives at the right hand end with greater speed?
Interesting. Ooh, I kind of like this question. It looks a little complicated, but I feel like it'll be.
I just off first glance, I would say block one. Like not even like doing physics, but I could just see it picking up speed like this. I think it'd have a greater velocity at the end of it. But
I feel like it would decrease a little bit of speed trying to get back up though, since it went so much lower than the other one, while the other one just has like a steadier decline.
I would say block two would arrive at a greater speed.
Right? I
Because
feel the same
once
too.
once block one arrives to the concave part of it, the speed actually decreases.
Yeah, as it starts to try to climb back up, it decreases. Well, technically, both of them. Well,
depending on
I feel like
on force too, but
true. Actually, right. So I fully agree. I was gonna say that they both might be losing a bit of speed. Only the block one would be losing more because it has to go up a higher hill. But then again, I'm thinking that block two is just a steady decline, and the only thing acting on both of them after you release them is gravity. And so gravity will have to work harder on, block one, since block one is gonna have to try to get higher. I don't know if you get what I mean. It's like the higher you are, more gravity to push you down and to get you way lower instead of, closer to the ground. So it's kind of what I felt like. So I agree with you, Alexandra, my bad, on block two.
thank you.
all right, so
would that be B?
it says that would be B.
For me, the first thing I noticed was this level right here. What they start, right? So extensional energy would be the same and exactly the same mass as well. At this point, I would just look for only an increase downwards, not a second increase. So this increase right here, it's not letting me write, I'm sorry. So this increase right here is this decrease is what I'm looking for. because this one would kind of be like two motions on the left. So motion one, getting to this point, and then motion two, picking up from here. So I'd kind of just like divide them into like two theorems, especially with the example that we just had about normal force acting on the object at rest with potential energy. So definitely a little different way than attacking it like you guys, but I feel like we arrive at the same answer, just picking that we know.
So what's our final answer here?
Well,
You want B?
Yeah.
I could see it.
I,
Let's
I
just,
feel like it's B as well.
because this one, like the
I'm
curved
okay with
line
B.
throws me off.
Definitely.
Oh, hold up, I have to switch out of, I'm gonna clear out drawings really quickly. Okay, it's C.
It's actually C. Okay, so both ducks arrive at the right answer with the same speed.
I think okay, so I was like thinking about this. So in the same way, they arrive, like they move from the same destination and arrive at the same destination relative to their first position, right? So we know that the distance travel, or like between the 2 points, the distance is, or at least the slope of the distance is technically the same. They travel from point Y1 and they arrive at point Y2. I don't know how much that would change due to the curve, but judging by the fact that they arrive at the same speed, what was the equation for speed again, Maria? It was over time?
For speed, it was distance over time.
Well, the distance changed is the same, right? They, like the amount of distance traveled, like overall is the same, or net distance. Because they travel from Y to Y2. I would say that their final velocity, like I can see why their final velocity would be the same because it just says what arrives with greater speed. But I would also think that block 2 gets there faster, which I think is what kind of screwed us up.
Yeah, I think we were looking at which one would get there first instead of speed.
Yeah.
I do believe that I understand why its speed would be the same at the point. I mean, if we look at it, we'd have just solving for potential energy itself, we'd have the same factors included in both Y1, Y2, and Y1 and Y2. So considering that they'd be the same factors as well as the same mass, that's why I'd say that the potential energy for both would be the same. So I do see why the speed. I guess it would be a great question to ask if it would arrive at the same time.
Yeah.
Yeah, true. And interestingly enough, though, I do feel like it wouldn't arrive at the same time, mainly because if you look at block 1, for some reason, I just feel like block 1 will, going down that super concave ramp, because of that, it technically has a little bit more potential energy than, potential gravitational than the other. But what makes them arrive at the same speed is the fact that it loses some of that speed while trying to go back up.
Yeah.
So if we just cut it in half, right, I feel like block 1 would definitely win in that case, because the concave allows it to go way faster and allows gravity to work more on it. But simply because it has to go back up, it loses some of that speed. Now, the fact that whether they reach the same time, like George says, is a very interesting question. But I do feel like if you just cut it right where you were trying to cut it right here, yeah, they would definitely not arrive at the same speed, because block 1 would be way faster.
Right?
Yeah, and if you cut the other one right there too.
You're looking at this difference right here.
You said what?
You're looking at the difference right there in the angle.
Yes, the difference right here, where it's about to climb back up to the angle. And so if you cut the other one at the same time too, at the same area, right? Let me join in on that.
Sorry about that, guys. It keeps kicking me out.
You're okay. You're essentially saying
So
like if it was
basically, I
cut
was
here,
saying
it'd
that
be
the way that
different.
you're looking at it is the angle coming off the x-axis being greater on the left side would make up for the fact that it has to dip back upwards. Is that what you think that they would get there at the same time, Sam?
Yes, simply
Sam?
Yeah.
I'm sorry. I was just asking, do you think that is the thought process here that I'm having correct? Do you think that it's this difference right here in angle that that would make it arrive at the same time?
Yes. I guess it would have more potential energy. I don't know if you guys can hear me, but
We can hear you better
it would
now.
have more. All right, perfect. It would have more potential gravitational energy working on it. I guess if you do cut it like right here, like I'm thinking
for this.
Yeah. We're saying like at that point, but like this is just hypothetical, and this is just showing our understanding.
Yeah,
But
for
yeah,
sure.
I'd
Just
agree.
hypothetical.
Yeah.
Mainly
Yeah,
because
definitely.
yeah, it would be having a different height, one from here to reach to here, in comparison, where if you cut that, it would be coming from here to here. And so, remember potential energy being proportional. This one having the more potential energy would end up reaching, more speed because of it. That's how I was thinking about it.
Yeah, and that makes sense to me. So yeah, I mean that's chapter 7. I mean that's chapter 7 also done. That's 7.5. That's essentially it, right? I'm not sure if we have too many more questions on that one specifically, but I think we covered enough.
Yeah.
Yeah.
Covered anything else?
Yeah, definitely for today. We can get together tomorrow and go over the rest, guys.
Yeah.
Yeah, for sure. I definitely agree.
So I'm gonna stop the recording now. To anyone who watches it, thank you for your time. And yeah, I'm just gonna stop it now.